Hello everyone and welcome to this lecture. Starting with this lecture, we're going to start looking at ordinary differential equations. Okay, so as we saw before in the very beginning of this course itself, that math is all about relationship between different variables, and initially we started with some simple equations, algebraic equations, quadratic, linear equations, all of that, which may be expressed relationship of one to the other. But usually in engineering, science and physical systems, time is a variable, right? So usually things vary over time, or maybe things vary over other quantities as well, but usually things vary over time. And when things vary over time, you want a relationship which also sort of captures the variation with time, the rate of change. How is the rate of change related to the original one, and how are all these things related? So once you go towards rate of change and write equations with that, naturally you will see many physical and engineering systems involve differential equations. So what are these differential equations? Let me begin by introducing them. So here is the definition for a differential equation. You have a function of x. F is a function of x. A differential equation is an equation which involves f, its derivatives, f prime, f double prime, and other functions of x. And these need to be satisfied for all values of x. Okay, so that's what makes the differential equation interesting, right? So you have f showing up, you have f prime showing up, f double prime, the rate of change of f with x, rate of change of f prime with x, things like that showing up, and then other functions of x. Okay, and then you will have to have an equation involving all of them, and that equation needs to be satisfied for all x. Okay, so it's a different kind of relationship, and we will look at techniques for how to solve simple such equations. But before that, I want to convince you that these kind of equations show up all the time in practice. Okay, so here are some examples, right? F prime of x equals 4. This could be one equation. F prime of x plus f equals 2. So notice this, I put a f here, that's of course f of x. Maybe I should change that. Okay, so here are a bunch of examples. You see f prime of x equals 4 is an example, f prime of x plus f of x equals 2 is an example, and then f double prime of x plus 2, f prime of x minus f of x equals sin x is another example. So you see these equations involve f prime, sin x, cos x, tan hyperbolic x, whatever. All these equations may involve all sorts of functions like that. And these are differential equations, and if you can solve them, can you solve them is the question. How do you go about solving them? How do you go about thinking of these kind of equations? It turns out there is a systematic way to do it. But before that, I want to just convince you very quickly by giving a few examples that differential equations govern much of the physical world as we see it. Most of the relationships fall down as an expression in terms of derivatives and all that. Things change over time, and you want to capture that change with respect to the original quantity and all that. So differential equations naturally show up in your analysis and study and science and engineering. Okay, so let's see some examples. Here's the first example, simplest example, one of the examples we started with when motivating calculus and rate of change and all that. Okay, so this is a falling object. Okay, you have an object here, which is an apple as I've shown here. Its position is 0, let's say, and then velocity is 0. It's at rest there, and then it starts to fall. When it falls, after some time, its position will become x of t. We can say the origin is here, and then this is the positive direction. So its position is x of t, and then its velocity or speed will be v of t equals x prime of t. So notice that x prime naturally shows up here, and this is a falling object. In fact, you know that from Newton's laws, the governing equation of this is actually a differential equation, right? What is that equation? V prime of t equals g, which is 10 meters per second square, roughly 10 meters per second square, or basically if you want to write it in terms of x double prime of t equals g. So these are examples of differential equations, and simple things like in a simple physical relationship like gravity and things falling due to gravity, they actually are solutions of differential equation. If you want to find x of t and v of t as a function of time, you have to solve these differential equations. So this differential equation is actually very easy to solve. We have seen the solution before when we studied calculus of motion and all that. So it's quite easy to solve. So you see here, directly integration will give you an answer, right? V of t is just x prime of t, right? You have to just integrate this guy. V prime of t is 10, so it will be 10t plus c1. Okay, so you have this constant c1. I'll tell you why this constant plays a role here, right? If you know v prime of t is 10, v of t is 10t plus c1. c1 can be anything. We don't know what it is. We'll figure out how it is soon enough. And then what about x of t? You just integrate x prime of t again. Okay, if you integrate this guy, 10t will become 5t square, c1 will become c1t, and then a plus c2, another constant will also add, right? So if you notice, this x of t satisfies both of these things. What is x prime of t? 10t plus c1. and then what is x double prime of t? It's 10. Okay, so this is very easy to solve because there was no complicated relationship between x prime and x itself. It was just all coming out to be constant. Okay, so you can solve this very, very easily. And to find C1, C2, use the initial condition, right? V of 0 is 0, right? If you put V of t equals 0 here, I should get 0 on this side. That gives you C1 is 0. Likewise, I fixed my origin here, so x of 0 is 0, and that gives you C2 is 0. So straightforward formula, x of t is 5t square, V of t is 10t. Okay, so we are able to solve this differential equation very easily, but we did this long before and we didn't think of it as a major equation because there was not too many difficulty in solving it. It's a very simple little example. Okay, so even the simple example of falling object is actually a differential equation. Okay, so you can solve this quite easily. Now it turns out, okay, so let's go back here. I'll give you a simple example. So supposing something is falling from a height of, let's say, 2 meters. Okay, 2 meters is not too far. And notice what happens to x of t. So x of 0 is 0, and if it were to take t equals 1 seconds, x of t is already showing us 5 meters, right? So in 1 second, I mean, usually the fall of 2 meters maybe is 1 second, okay, or maybe even lesser, but still notice x of t goes off to 5 seconds, okay. Why is that? And also, I mean, look at the speed, you know, I mean, in 1 second, you're not going to hit speeds like 10 meters per second, okay. So in real life, falling objects meet another thing called air resistance. Okay, so because of air resistance, you don't quite fall purely in gravity. If everything were a vacuum, there's no air, then you fall freely, right? But if there is air here, air will resist the flow. Okay, air will resist the fall. Okay, and how do you model that? A very popular way to model that, of modeling air resistance, is like this. Okay, supposing an object is falling down with the speed of v of t. Okay, what are the forces acting on this object? There is a mass because of which there is a weight mg. Okay, and it turns out there is air resistance, which is some k is some constant, okay, some factor, could be 0.5, could be 1, whatever, multiplied by v of t. So the resistance of the force for small objects, at least, maybe not even as big as an apple, but small enough objects, the resistance is proportional to the speed of the object, and it is against the direction of the speed. Okay, so in this case, velocity's direction is downwards, so air resistance is going to be upwards, and it's going to be proportional to v of t. Now this has been observed several times in physics, and this is the correct model for an object falling in air with air resistance. Okay, now when you have air resistance like this, your equations governing the motion change dramatically. What happens to Newton's laws? You know that the force, net force acting on an object, what is the net force acting on this object? It's mg minus kVt, right? Mg minus kVt, it's a net downward force. That is going to be equal to mass times acceleration, isn't it? That is Newton's law. The net force, which is mg minus kVt, is equal to mass times acceleration. Acceleration is v prime of t. Or you can move this around and notice what equation you have here. V prime of t plus k by m v of t equals g. So previously we didn't have this term, right? If you ignore air resistance, this will not be there. So it was very easy to solve. Now when you have this, I don't know how to solve it very easily, because there is v prime of t and then v of t. Okay, how do you solve an equation which has both v prime of t and v of t? And this is something that's going to happen in practice a lot with air resistance. Everything is falling in air, so you have to take this into account. Okay, so we have seen here speed of a falling object is the solution to a differential equation in the realistic case of incorporating air resistance. Okay, so that's one example. Here's another example of familiar RC circuit with a DC source. Okay, so you have an RC circuit here, and maybe there is a battery connected to it, 5-volt battery, and you're going to turn the switch on at t equal to 0. Maybe a capacitor has no charge initially, so it's all without charge, so you have a resistance R, capacitor C. Now the current here is going to be a function of t, I of t. How do you find I of t? I mean, I of t for t equal to 0, t less than 0 is going to be 0, right? Yeah, that's true. So, and through a capacitor, current is not going to suddenly surge. So, you're going to get I of t equals 0. So, at t equal to 0, you may know something about the current. Let's say you know something about the current. Okay. Now, how do you find I of t as time progresses? So notice physically there's a lot of things happening here, right? So, when you close the switch, you know, charge will start flowing in this direction, and the capacitor will start getting charged, and as it gets charged, it will start resisting the flow, right? When the capacitor has a charge, the current will not flow quite as easily as it did before. Eventually, finally what will happen? This entire 5 volt charge will show up around the capacitor and current will go off to 0. Okay, so this current is going to be something in the beginning and it will go off to 0 at the end. Okay. So how do you deal with this current, right? So like I said, I mean, I of 0 you may know from the circuit characteristics, but you know that eventually when t becomes very large, I is going off to 0, right? So initially there is some flow of current and then eventually at the end I is going to go off to 0, right? So knowing these things, how do you find the exact way in which I of t behaves? How do I find I of t as a function of t? For which you have to write down equations with the circuit laws. Here is the circuit laws that I am going to write down. The voltage drop across the resistor at any time t plus the voltage drop across the capacitor at any time t has to be equal to 5. Right? So this is a basic circuit law. This is Kirchhoff's loop law or something like that, right? Loop equation that you can write down. Then what do I know about Vr of t? That is R times I of t. And what do I know about I of t through the capacitor? I of t is C times Vc prime of t. Right? The rate of change of voltage is related to the current, right? I of t is C times Vc prime of t. Okay, so these are the equations that I know. Now I can plug this back in, but how do I plug it back in? I have the Vc prime, right? How do I do that? I'll have to differentiate this equation, no? You can differentiate this equation, then you can plug everything back in, right? So if you differentiate that equation, okay, and do some manipulation, right? So you will get, Vr prime of t is R times I prime of t plus Vc prime of t is 1 by C times I of t and then equal to 0. And then you divide by R, you get this equation. So what you get here is a differential equation, I prime of t plus 1 by RC I of t equals 0. And then I of 0 equals, I've put a question mark, I of 0 will end up being 5 by R. Okay, so initially, when it starts, the current is going to think the resistor is the only thing there, and I of 0 will actually be V by R. And then you'll have to solve this differential equation to find out how I of t behaves. In I of t, I told you eventually it goes to 0, right? It starts at V by R, 5 by R, and then it goes to 0. How exactly will it go to 0 depends on the solution of this differential equation. So current in an RC circuit with a DC source, when you turn on the supply, turn the switch on, you're going to get a differential equation to govern the characteristic of I of t. To find I of t, you get a differential equation. Okay, so a differential equation comes in a falling object. With that resistance, differential equation comes in the charging of a capacitor, current when there is a capacitive influence on the circuit. Okay, so this is not the only case. So you may have a AC source, right? You may have a 5 sine omega t here. In that case, notice what happens. Vr of t, the same equation sort of holds, except the 5 becomes 5 sine omega t. So now when you do the differentiation and all of this, on the right hand side you won't get 0 here. You will get I prime of t plus 1 by RC I of t equals 5 omega by R sine omega t. So I put here I of 0 is 0. In this case, this might be true because sine omega t, but anyway, I mean you don't have to, you need something about I of 0. I put 0 here. Maybe there is this entirely not correct, but anyway, you will get this here. So I of 0 is somehow known, and from that you have to solve this differential equation and get that. So current is the solution to a differential equation in many of these RC circuits. Now you can imagine, even if you have RLC circuits and RL circuits, you will have this kind of a situation. Okay, so we see circuits, to be able to solve circuits, when you have time varying currents and voltages, you really need to know differential equations. Okay, finally, I'll show you a completely different model, completely different problem. Okay, and again differential equations show up. Okay, so in this model, it's an ecological problem. Okay, what is ecological problem? You're tracking the population of a species of animals, let's say animals, birds, whatever, over time. Okay, and you think the population of the species at some particular time t is n of t. T could be some units. It doesn't matter what the units is. We'll think of it as a continuous variable for being for simplicity. Okay, so n of t is my population of species at time t. Now I'll be interested in what n prime of t is, right? What is the growth rate of the species population? Is the growth rate positive? Is it increasing? Or is the growth rate negative? Is the population decreasing? Whatever it may be, it's very reasonable to assume that the growth of n is proportional to n itself. Okay, why is it reasonable? Because how does population grow? If there are more animals of a particular species, they are going to reproduce, and when they reproduce, the population grows. That's the growth rate. Now, if there are more animals, the more they're going to reproduce. So it makes sense that n prime of t has to be proportional to n of t. Okay, so that is one fact, So you see, you expect that n prime of t will be proportional to n of t, and maybe there is a constant here. Now population cannot keep growing forever, right? Because for that animal to be born, that's not enough to, it needs to grow up. So it needs to be able to eat something, it needs to be able to consume it, all of that should be possible. It should not have predators, it should not get disease, all these factors are there. So if there are too many animals beyond the capacity of a certain place, that can, how much animals it can take, then the animals will start dying. Okay, so the growth rate is going to decrease if the population becomes too much. Okay, how does that model? And how is that modeled? That is modeled as some sort of a capacity. You think of K as a maximum sustainable population in a certain area. Okay, maybe it's a forest or something, or some ecosystem, and you have a maximum sustainable population. Now, if n is small, and what you think of is this growth rate is going to be proportional to 1 minus n of t by k. What does that mean? If n of t is very small compared to k, this will not have an influence. N prime of t is just proportional to 1. It will just be dominated by this guy. So if n is small, n of t grows very fast. Okay, and as n increases, gets closer and closer to k, like for instance, if n of t is equal to k, this is going to become 0, and then growth rate simply stops. Okay, when it goes closer to capacity, the growth rate is going to be reducing lower and lower, and if in fact n of t is greater than k, then the growth rate could go negative. It will have to reduce over time. Okay, so these are interesting and simple observations, and all of these are encapsulated into one differential equation. Notice this is a differential equation. It involves n prime of t and n of t, and this is a very popular model in population study. N prime of t is r times n of t times 1 minus n of t by k. Notice this has all these desirable properties. When n is small, n of t grows fast. Okay, when n is close to k, n of t starts growing slower, which is what you expect. And if n is equal to k, growth rate is 0, and if n is greater than k, growth rate is negative. So all of these are nicely fit here, and you use this formula and model to calculate r, and then r tells you something about whether the population is sustainable, is it going to grow, is it going to die out, is it going to go extinct, should we interfere, etc., etc. So interestingly, population of a species is also solution to a differential equation. So these kind of things are done in practice everywhere, be it physics, be it engineering, be it ecology, wherever, any model you take, people bring in these differential equations and solve them. Okay, so let's look in general at the first order linear ODE. Okay, hopefully I've convinced you that the ordinary differential equations are going to show up everywhere in the world that you see them, and you have to solve them. Particularly in circuits, they're going to show up all the time, and you should be comfortable with solutions to those equations. Now let's first look at a class of ODEs that are reasonably easy to solve. Okay, so these are called first order linear ordinary differential equations, and they have this general form. Okay, what is the general form? F prime of x plus p of x times f of x equals q of x. Okay, so notice here you have f prime of x showing up. This is why it's called first order. Okay, the maximum derivative that shows up here is derivative of order 1, f1 prime of x, right? And then f of x of course shows up, and then there are these two other functions, p of x, q of x. In most of the problems we have, this p of x will be a constant. Okay, so you'll see p of x will be a constant, but this q of x may not be a constant. You will get different possibilities here. And f of x is what you have to find. There's an equation here. This p of x and q of x are given. Of course, p of x and q of x will not depend on f, right? So these are different from f, but this f prime and f of course depend on f, and these have in this form. So this is the general form of an equation. I just want to show you all the examples we saw fit into this form. Okay, so if you look at falling object with air resistance, v prime of t plus k by m v of t equals g. So f prime is there, f is there. What is p of t? It's k by m, it's a constant, and q of t is also constant, g. Okay, so this is the most interesting case, constant coefficients, linear ODEs. These are the nicest possible things. We'll see solutions for them particularly. But you may also have a more general RC circuit, like for instance I prime of t plus 1 by RC I of t equals Vs of t, right? So some Vs of t which is related to the source. It could be a constant, it could be 0 for instance, or it could be some cos omega t or any other shape that you have. But p of t, if you look at it, is 1 by RC, so that's a constant. Okay, so you don't have this varying with time. Okay, so these two are examples of what we call as first order linear ODE. Now in contrast, the population model is not linear. Okay, so it's again a first order model. Okay, it's first order because the maximum derivative that shows up in this equation is only 1. Okay, so that's first order. But it's not linear because this n of t is getting multiplied by 1 minus n of t. So you have n of t squared showing up somewhere. So this ends up being a non-linear model. We'll mostly look at linear models. We won't bother too much about non-linear models. But it turns out this model itself is solvable. Okay, so it's not very difficult to solve. But nevertheless, our focus will be primarily on equations of this type. Okay, so let's begin our study starting with the next lecture. Thank you very much for your attention.